UARC, CompArc concepts. I'm going to go through this allocation chapter real quick. Decode I skipped, and I'm probably going to skip a few chapters here because it's just talking about like x86 semantics. More specifically, decode, you just take basically the fetch instruction and then you kind of create a bunch of different control signals with it. That's kind of like the high level idea. There's not much here that's not just pure memorization, and I don't think an interviewer would ask this because if you're actually working at like Intel or AMD where you have to do x86 stuff, and it means like you're very specifically on the decode team. But if you're on the decode team, you generally can just download a PDF that, like the x86 IEEE spec, and you can just look at that and do your implementations. Like memorizing this stuff doesn't really do all that much for you. And if an interviewer like needed you to memorize like these very, very niche specific stuff, that's not really like high level concepts. Probably not a great team to work with. But allocation, on the other hand, is more about like a high level thing, and it's kind of more universal to computer architecture. So let's go through that. So allocation is just basically, so before you can issue your instructions to execute, you need some source and destination registers to read and write from, right? So allocation takes care of that. And the tricky thing about allocation and register files and stuff like that is you can have these data dependencies as well as false data dependencies. So if you have a data dependency, aka a raw hazard, then you actually have to wait for this very first instructions to dump its data into R1 before this guy can execute, because you can't really predict what the data is, right? So you wait for data to come back and you execute this other instruction. Now there are false dependencies where you have these write after write, where you write the same register with respect to the software view, but it's really referring to something else because all the instructions after this guy referring to R1 isn't really referring to the same value as this R1, right? But you can see that between these two instructions, if there's any consumers of R1, then it's referring to this R1. So here, you want to quote unquote overwrite this R1, but the issue is you could be executing instructions after this instruction and some instruction here at the same time, meaning you need both views of R1 at the same time. And then here we have a write after read dependence. So for example, since we're out of order execution, we can execute this first before this. So how do you make sure that, when you write to this, you're not actually overwriting this? So that's where allocation and renaming and everything comes from. So one can do renaming by basically mapping these R1, R2, whatever registers, the R1, R2 being registers with respect to what software sees, to registers with respect to what hardware sees or internal to hardware. So you can kind of think of it as like, these architectural registers are, these software registers kind of analogous to virtual addresses, and these internal like PRF register file registers or named registers inside the CPU is going to be more analogous to like physical addresses, like internal to the hardware, right? And kind of decoupling the software register naming with the hardware register naming. Right, so the first way that you could do renaming your registers is actually not really to really rename it at all too much, because there's no free list here, as you can see. So what you could do is you could just have a map table, and there's still a mapping. You can have a logical register, and technically these are not like register names, but your logical register can basically point to the reorder buffer. Reorder buffer are for everything in flight. It's for everything that's still in flight and not yet committed. And the register file is the committed architectural state, like the permanent state that's in the computer. So your logical register file can point to this map table, and this map table can say, well, does this currently exist in the architectural register file as the most up-to-date, or does it exist in this in-flight? So if it's in flight, then there's a reorder buffer entry that's holding the value, and if it's already committed and kind of like there's no in-flight or hazards or anything like that, then it'll just be in the architectural register file because it's already committed. So this switch says pick from this one or pick from this one, and then if you do pick from this one, there's kind of a convenient field here for you to look it up directly in reorder buffer. So in this way, if it's talking about this R1 or this R1 or this R2 or this R2. So this is like in flight, and I know that this entry is an older entry of this entry, and you can tell this is older because the reorder buffer is in order. Then you won't take the R2 from here, right? And then you would just take the R2 from the architectural register file instead, right? So this is one way to do it, is to just pick between in-flight or committed, right? Because there's really only the two places that it could be, or it doesn't exist yet. In which case it would need to go in flight at some time. This is just talking about rename buffer, which is just using a different FIFO structure for it. But this merge register file is kind of like the canonical scheme across most CPUs I know of nowadays, and it kind of just involves a couple of structures. So one, you have a universal register file as opposed to these two places where you store values. So there's only one place for all your values. And then now here's kind of the more like the analogy I talked about earlier, where you have a logical register mapping to a physical register ID. So this is just a mapping between software register or hardware register. You can think of it like that. So software register will look up where the hardware register is, and then I will look up the value via the register file. And then so how do you do this? You do this vis-a-vis what's called a free list. The free list will just basically generate new entries, new physical register IDs, given what's available in this rotating buffer. So every time you allocate a new entry in the register file, you're just going to take up an entry in the free list. And so for example, here's a good example. This R1's renamed to physical register 1, and then this R1's renamed to physical register P5. So now internally they look completely different. And a consumer would only have P1 in one of its actual sources if it's actually, there's a raw hazard of the data dependency, in which case there's nothing you do about it. But then this renaming helps us break that false data dependency. And then everything below this, using this specific instance of R1, would then you just use P5, right? And then so when do you deallocate it? So you would deallocate it when this instruction commits. If this instruction commits and this R1 is final, that means everything above it has committed and finished as well. And ergo, you can finally free up this P1. So I think it says here, in this example, P1 is released when this P5 and like this instruction completely commits and retires. And the reason why you can't wait for just when this is fetched and everything above 2 is committed isn't enough is because if you have an exception, and let's say you have an exception and you have a branch mispredict, instead of using R1 equals R4 times R5, what if now instruction 2 actually does require this R1? Then you actually still need that value in your register file. Whereas if this has actually finally committed, then this necessarily means that this value has been officially overwritten, and if it's officially overwritten, then you don't actually need to be able to ever there's no more instruction that can possibly be able to use this P1 again. So that's kind of like the tricky thing. But then the good thing here is that a register file, right? Like if you have like 100 of these registers, then then your register file is only on the order of hundreds. Yeah. So like double or triple the size of this, right? of the namespace of the software thing. Yeah, so I hope that makes sense. That's kind of like the renaming portion that will break data dependency and like wall and write after write and write after read hazards. So here it's talking about whether you should read the register file before you issue the instruction or right after you issue the instruction. So if you read it before issue, then your scheduler needs to suck in the values from the register file. But if you're reading it, and then you have to keep extra copies of the values. And then if you read it after issue, so like you issue it, you just know that all the data dependencies have been satisfied. You parse it out to the ALU to execute the instruction. The instruction needs source A and source B. Then the ALU just requests it directly from the register file. Normally the latter is a little bit better, just for simplicity's sake. But I think this here makes the argument that you might want to do read before issue if you are going with this scheme instead, where you just make an extra copy. Yeah. Yeah, this is kind of like a really nuanced point. I don't know that. Yeah, I don't know that it's like worth too much investigation or memorization of this. Just know that you can issue it, like you can read it inside the scheduler, which means you have extra space in the scheduler, or you can do it in ALU. Yeah, doing it in the ALU is a little harder to pick between the reorder buffer and the arc register, because then a lot of the control information where all the dependencies are like less accessible, and you kind of want your ALU to start executing already, where the scheduler is more controller logic heavy. Okay, yeah, so this talks about recovery. So chapter 8, it will talk about this more, so I guess I'll go through that more. But basically, you can have a very area aggressive thing where you snapshot your architectural registers and when every single new instruction is encountered, or you could just rewind by leaving breadcrumbs as you rewind the reorder buffer. And then you can kind of just Control Z a bunch of times until you get to the part of the instruction where the exception no longer applies. Here it's a comparison of the three schemes where you do the reorder buffer plus the arc register and then the rename buffer. They're both FIFO structures, and then you can also do the slightly more complicated but actually more convenient by using a free list and a unified physical register. Yeah, so I guess their argument is that this is more complex, but I kind of disagree. You have more structure doesn't mean it's more complex. It's actually more simple. Because yeah, again, like they kind of talk about here, it's easier to maintain because the register value is just written once and never move. Whereas with the other two, you need to have two copies eventually. One in the reorder rename buffer, and then later in the committed arc file. So it says extra energy consumption, but op completion is like such a rare thing compared to like the rest of execution. I don't think that this matters too much. I think just keeping multiple copies of the same thing in hardware is just prone to more issues like parity errors, and it's just going to be harder to tape out a chip, which this really doesn't talk about. Like this, keep in mind this PDF is like lectures, right? So it's just like highly theoretical, but if you're trying to build a chip and you want to tape it out in like 2 years, you'd much rather have more structures and more area and slightly more power even. In this case, it's less power, but But I'm saying like you can make those trade-offs if you can be more sure you can take on 2 years for the company as opposed to creating super optimized complicated code that would take like, delay the project by like 6 to 8 months, which doesn't make any sense, right? Because if you delay a project by 6 to 8 months, you lose way more money than if you were to squeeze an extra like 0.05% of performance. Um, so those are the actual functional like business kind of trade-offs that someone with like good engineering experience would keep in the back of their mind, and you would see that a lot of juniors just try to like over optimize things and there's a little bit more power. Yeah, it doesn't matter unless you uh yeah, like only the people that like graduated with textbooks really care about it, and then they realize it's a lot to maintain and things take a lot longer um, than they were expecting. Um, so yeah, I guess here it's actually talking about like read after issue, read before issue, no real significant changes if you have a merge register file, because I guess they're coming in the same place. So I guess I take back what I said before, what I thought this thing said. On the other hand, if you have a bunch of copies everywhere, then you want to read it before issue. But why? The challenge comes from the fact that register values eventually move from one location to another. In the read after issue scheme, source identifier the source operands. I see. So basically it's saying if you read right after issue, what happens if the identifier, like what happens if that thing moves from the reorder buffer to the architectural buffer right as you issue it. Whereas if you do it before issue and you make sure that you got all the values before you issue it, then you're hunky-dory by the time you execute. Yeah, so this kind of goes back to what I was saying, like your scheduler or your issuer, whatever you want to call it, already has all the control logic and all the information. So it's a lot easier to communicate with other heavy control logic things like the reorder buffer and the commit register than unnaturally have the ALU try to tease that information out, because that's just going to be a lot harder. But if you have unified register, you could make a copy in your scheduler and then issue it, or you could just do it just in time and then just have your ALU read it. I wouldn't. Yeah, I mean, if you have a merge register, meaning you have a PRF and a map table and a free list, I would probably just read after issue, because why would you want to have all these extra entries for basically no reason? Going to your previous point, you don't want to over optimize stuff, but you don't want to just like trivially add area for no reason, right? And in this case, if the implementation is about the same and it's not going to be really any more difficult or any more easy, you might as well go with the option that saves you a lot of flops. This is just talking about how hard it is for like after issue to find where the proper information is. This issue stage, I might be skipping some chapters like the issue and execute, because I think I skimmed it, and a lot of it is like very specific, especially execute, like ALU stuff, like how does a multiplier work, kind of a stuff. But yeah, I mean, I'll skim through this and then see if it's worth covering. It's also a bit longer. I will go through commit stage, because I think retiring an instruction and how to handle exceptions, those things are more higher level computer architectural concepts. Whereas with how your scheduler works specifically and how you parse it out to your execution units is going to just be very implementation and project oriented. Like this could change from project to project. Same for execution. Like you could have multipliers of 42 compressors, 43 compressors, like whatever you want, right? Like just depends on your project and what your specs are. Commit stage is more universal across all projects, because you like, as long as you're doing Neumann, which is everything, you need to retire the thing and commit it to memory in some way. So it's kind of across all chips, as is handling exceptions, right? All chips need to handle exceptions, and committing and rewinding and making backup copies. Those are, real consideration and trade-offs across, pretty much any running computer. Whereas I feel like execute issue, it's so specific that it might not be worth covering because no one might ask for it. But yeah, hopefully the allocation stuff made sense. Yeah, and that's all I have. Let me know if there's any questions about allocation in the comments. Happy to answer, and it'll help me study as well. Thanks.